To engineer a system capable of turning millions of gallons of water into megawatts of electricity, you have to map exactly how fluid kinetic energy is converted into mechanical work. Every force generated by a fluid jet relies on Newton's second law, but instead of applying force equals mass times acceleration to a single rigid object, we apply it to a continuous stream. This control volume diagram shows mass flow vectors. Engineers calculate mass dynamically as mass flow rate, the product of density, area, and velocity. For exams, remember, the force exerted by the jet equals the force changing the fluid's momentum. Mastering this impulse-momentum relationship provides the basis for all advanced turbine design computations. This diagram establishes our baseline engineering test case, a static vertical plate struck by a continuous jet. Because the plate is stationary, its velocity is zero. The fluid strikes the wall, transferring all horizontal momentum, generating a force equal to density times area times velocity squared. However, work is defined as force times distance. Since the plate does not move, the mechanical work done by this system is zero. This schematic compares a flat plate to a stationary curved vane. To increase structural force without introducing motion, we alter the geometry. By curving the blade to deflect the jet a full 180 degrees, the structure actively reverses the fluid's direction, doubling the momentum force. While a curved blade maximizes pure structural force, a stationary system produces no usable power. To generate work, the target must move. When the target plate moves away from the nozzle at velocity u, the variables change. This diagram highlights relative velocity. The jet no longer strikes with its absolute velocity. The impact velocity is the difference between the jet speed and the plate speed. This velocity difference dictates the mass striking the plate per second. Density times area times the relative velocity, v minus u. Applying this relative mass flow to the momentum equation results in a new force formula, density times area times the square of the relative velocity. To find the mechanical work, we multiply that force by the plate's velocity, u. This is a frequent area for errors. You must distinguish between the squared relative velocity in the force equation and the single u multiplier attached to the work equation. Even with the correct math, a single moving plate cannot provide continuous power. The jet eventually outruns the plate, and mechanical work drops to zero. To maintain power generation, turbomachinery uses a continuous, unbroken series of vanes attached to a rotating wheel. This diagram models a continuous system. Because a new vane constantly rotates into the flow's path, the wheel intercepts the entire nozzle jet mass. This creates a critical distinction. The mass flow rate reverts to the absolute velocity equation, replacing the single plate relative mass calculation. Combining this absolute mass flow with the relative velocity impact provides the finalized work done per second for a continuous system. With a continuous system established, we can calculate the specific wheel speed required to extract the maximum possible kinetic energy from the jet. This slide shows the calculus derivation. Setting the derivative of efficiency with respect to u to zero reveals the mathematical peak. For flat vanes, maximum efficiency occurs when wheel velocity is exactly half the jet velocity, capping efficiency at 50%. To exceed this 50% limit, engineers must combine a continuous series of vanes with curved geometry and radial directional flow. In many industrial applications, fluid travels radially across a spinning wheel, moving from an inner radius to an outer radius. This schematic of inward radial flow illustrates the mechanical change. Because linear velocity is the product of angular velocity and the radius, the blade speed is different at the inlet than it is at the outlet. Because the flow is radial, linear force is replaced by torque, which is calculated using the rate of change of angular momentum. This velocity triangle isolates a new variable, the velocity of whirl, the tangential component of the fluid's velocity responsible for generating rotation. Integrating this tangential component gives us Euler's equation for torque and the resulting formula for work done per second. This formula is used to determine the overall hydraulic efficiency of the system. For exam purposes, a critical shortcut is available. If the discharge is purely radial at the outlet, final velocity of whirl is zero. Setting that variable to zero reduces the efficiency equation to a simple product: mass flow rate, initial velocity of whirl, and initial blade speed. Euler's angular momentum equation scales the impulse momentum principle to the rotating systems used in modern hydroelectric dams. Solving turbo machinery problems requires recognizing how the fundamental variables change across these four physical states. This matrix synthesizes those states. Notice that the mass flow variable uses relative velocity for single plates, but returns to absolute velocity for a continuous series of vanes. Even with the correct formulas, test makers often use three specific traps to cause errors during calculation. The first pitfall is weight versus mass. If a problem provides specific weight instead of density, you must substitute specific weight divided by gravity into the mass flow rate equation. The second pitfall involves angle definitions. You must determine if the given angle is the angle of deflection or the angle made with the plate. If it is the latter, subtract it from 180 degrees before proceeding. The third pitfall is unit conversions. Area must be converted to square meters, and you should use the standard density of water at 1,000 kilograms per cubic meter unless another value is provided. Applying the kinematic shift alongside these three execution protocols creates a consistent method for solving any hydraulic machine problem on exam day.